Okay, so I apologize for today's class. My car has some problem in the middle of the road. It's overheated, so I have drive and stop and get here so late. And I prepared this video and hope you will have time to watch it. And I also going to talk about today's class with the department and see if we can make out today's class sometimes later before the finals. Alright, so I'm going to just use this video to finish Chapter 11. We talk about this slide Tuesday in the class. So we are going to study the so-called dispersion force. Dispersion force is one of those intermolecular forces, and it depends on the molar mass and depends on the shape of the molecule. So in general, as the molar mass increases, the dispersion force increases, and in terms of shape, when there is more contact surface area, there will be a stronger dispersion force. But the dispersion force is only one of the force. When you consider some of those macroscopic index, for example, melting point, boiling point, you have to consider all those possible intermolecular forces. In this table, you see the pattern is, or the comparison is about the boiling point for those noble gas atoms. And you can see the helium, neon, and as you go down, like from the top of the group, go to the xenon, the boiling point increases. So that's the boiling point is very good indicator about the intermolecular forces. So therefore, we can see the intermolecular forces for the noble gas atoms as they go from the top of the group of helium and go to xenon, the intermolecular force increases. And then we know the only intermolecular forces for those noble gas atoms is the dispersion force. And so therefore it's a good example for us to compare the effects of the molar mass on the dispersion force, because the dispersion force is only intermolecular forces, and the increasing pattern of the dispersion force for those noble gas atoms is indicated by the increasing melting point. So as we talk about, there are two variables or two factors that will influence the dispersion force. One is the molecular shape. And you can see these two molecules called the isomers, and both the two molecules has 5 carbon and 12 H. So those are the isomers because they have the same molecular formula, but they have different structures. The molecular formula for both is C5H12. Alright, so then this first molecule looks like the shape looks like a rod, and then the shape for the second molecule looks like a spherical ball. And you can see then the contact surface area for the spherical shape molecules is very small. It's only in this part of the region. And for the rod molecules, so somehow when you like arrange the two rod molecules like two markers, and you line them up together like that, and you will have more contact points than compare with contact points between two spherical balls. Alright, so these two molecules has the same molar mass, so therefore the other difference is the shape, and the shape determine which one has more surface area or more contact surface area, and this one with some arrangement in more. So therefore, for this N-pantene, it will have a larger intermolecular forces. And then you want to compare, measure it, and I will surface you can measure like the melting point and boiling point, or vapor pressure, or viscosity, surface tensions. So then you will see some of those patterns, but you want to connect the pattern with the dispersion force, then you have to make sure the other force is not exist, but the other force are the same. And so then we did not study too much details about other forces yet. The other forces is dipole-dipole interaction and ion-dipole interaction, hydrogen bonding. So for all the other forces, except the dispersion force, both of these two molecules they don't have. So the only force, the only intermolecular forces for these two molecules, for these two types of compound, is the dispersion force. So therefore, if we can measure the boiling point, and if we see the boiling point of this one is higher, then that's good. That means because there are no other forces, if this boiling point of this one is higher, which means this has a stronger intermolecular forces, and the only intermolecular forces for both of them is dispersion force. So then we can come up with conclusion the dispersion force for this one is larger. Then we were connecting or make some reason why the first one, this normal painting, has a larger dispersion force, is because those kind of shape give it more surface area or contact point. Yeah, you can see the data for the new painting. The boiling point is 36.1 degrees Celsius, and then the boiling point for this one is 9.5 degrees Celsius. So that is a good indication, and the shape really is a variable that will influence the dispersion force. Right. So there are a few more examples, and so this example, this practice is to choose from each one pair of those compounds, which one will have a higher boiling point. And as we talked about before, the boiling point, we can call that a BP, is proportional to the IMF. IMF standing for intermolecular force. Okay, so I is inter, M is molecular, F is force. Right. So you want to compare the boiling points, so therefore you have to compare the intermolecular force or forces depending on what type they have. And so we talk about the intermolecular forces. There are a few types, and then we talk about those relative strengths. And precisely, when you compare those strengths, you probably want to think about the strengths per gram or per kilograms. So the dispersion force is the one that is relatively weak. And you will see there is a table later on, and so those are types of the intermolecular forces, or IMF types, and then we can see what are their relative strengths, and then we can see for what type of material. So this relatively weak, and for all type of materials, and so then you will see the other forces that become stronger and stronger, and the strengths. So as we said, probably you want to add in something like per gram or per kilogram. So in terms of that, this dispersion force is the weakest. And the next type is dipole interactions, dipole attractions, and so that become stronger, but it's kind of selective. It's not for all type of material. It's only for those polar, for the polar molecules. That means the material must have those molecular that is polar. And the next one become even stronger. It's called the hydrogen bonding. Even stronger, but it become more selective. It's only for those compound that has H bonding to F, or H bonding to O, or H bonding to N. So it's only for this. In this class, we only talk about the hydrogen bonding for these three type of compound that has H chemical bond bonding to fluorine. Okay, so these are the chemical bond. And when we talk about the hydrogen bonding, it is not a chemical bond, but it is IMF. So the name may be a little confusing because of the hydrogen bonding, but you have to keep in mind it is not really a chemical bond. It belongs to one type of those intermolecular forces. It's become stronger than dipole-dipole, than usual dipole-dipole. It's stronger than dispersion force. So far it becomes the strongest, and then we will have another stronger one. But it's more selective. It's only for those compound that has HF. I mean, one of the compounds is HF. Then some other compound has the H covalently bonding to O, and then what's the other side of the O bonding to doesn't matter. It can bond to another H, or bonding to carbon, or bonding to what else. As long as you have the H bonding to O. So for those kind of material, you can have the hydrogen bonding. But whether the hydrogen bonding will dominate the intermolecular forces, that depend on those per gram, depend on what is the mass of the molecule and how many of those H and O hydrogen bonding you can have. Okay. So then the last type of compound that can have the hydrogen bonding is H bonding, again, covalently bonded directly to N. Okay. So this is sometimes an easy confusing point. And people will say, if you have H and F in your molecule, you think about you will have the hydrogen bonding. No, not necessarily, not always. You have to check. You have to see if H chemically bonding to F. Similarly, if you see your molecule or your compound has H and O, and you just come out very quick, come out with conclusion and say your compound has hydrogen bonding, but you might be wrong because you have to check that the H must bond covalently directly to the O, and then you can have the hydrogen bonding. Okay? And similar for the H and N. All right. So when you compare those boiling points, melting points, vapor pressure, viscosity and surface tensions, all those have some connection with the intermolecular forces. Okay? Now this boiling point, that means directly proportional, which means if the IMF, the strength increases, your boiling point getting higher. Okay? You will have a high degree of temperatures. Okay? Right. So then you want to compare those two pair of compounds here, and you have to think about all those possible forces. Okay? Now so far we see these three forces. Okay? Now one last force that also called the intermolecular forces is ion dipole attractions. And so then in terms of the strength of the IMF, the ion dipole attraction, it will be the strongest. But it has this requirement. It's for those ions. That means you have those ionic compound and polar molecules. Alright, so this is the last type of intermolecular forces, the so-called ion dipole forces. It is the strongest of these four. If you want to number this 1, 2, 3, 4. So these 4 types of intermolecular forces. The ion dipole is the strongest. And it only for those compounds, or between those compounds, that is ionic compound and polar molecules. And it's very important intermolecular forces. And this basically is the force that dissolve some of those ionic compounds, and we studied in chapter 4 and previous chapters. So some of those ionic compounds, we usually call them salt, that is soluble in water. If they are soluble in water, and the force, that is the intermolecular forces, that is responsible for that solubility, measured is the ion dipole forces. And now we can compare the ion dipole forces with the 4 intermolecular forces for the solvent and intermolecular forces for the solute. And we know those solubility rules we studied in chapter 4 is kind of empirical. And if you study chemistry 1 and 2, and you can just do a little more advanced calculation that will depend on the Gibbs free energy change for the solution process. But so far we will see, we will go back to chapter 11 and concentrate on this these 4 types of intermolecular forces. So when you consider when you compare this boiling point for different compound or different elements, you have to keep in mind to check if we have all those other forces. Right. So now let's go back to the problem. The first pair is methane and butane. So both of these 2 molecules are nonpolar. We studied from chapter 10, and you can just check these 2 molecules. Both of them are nonpolar because in those 2 compounds, the only chemical bond we have is CH or C2C. And according to what we studied in chapter 10, the electronegativity between C and H is not large enough to have a chemical bond that is polar. So that means the C to H bond is a non-polar bond. And obviously C to C bond is not a polar bond. Right? So then according to that, the minimum condition to have a polar molecular is to have a polar bond. If you don't have a polar bond at all, no matter what the geometry you have for the molecular, your molecule is nonpolar. Right? So both of them nonpolar, and so that all the other 3 forces except the first one require you have those dipoles or have those polar molecules. Right? So therefore, for the first pair of molecular, the only force we have is the dispersion force. Now, dispersion force, as we studied in the previous section, depend on 2 variables, depend on the size, depend on the shape. And so the size of this second molecule is much larger than the first one. Just when we see the size, which means you can think about the mass or the molar mass for all those compounds. And for the second one, you have 4 carbon and 10 H. For the first one, you will have 1 carbon and 4 H. So in terms of the size, it favors the second one. And then you talk about the shape. So the shape of the first one is just like 5 atoms bonding together in a tetrahedra. molecular geometry. It's kind of like a spherical ball, and this one is again is a rod. So both variable or both factors favors the second one. So the second one will have a higher, a stronger dispersion force, and both of them have no other intermolecular forces. So if this one have this stronger dispersion force, which means this one will have a stronger intermolecular forces. If this one has stronger intermolecular forces, that means this one will have a higher boiling point because these two are directly proportional. Right. So then we can compare the second pair. The second pair, we have this C6H12, and one possible molecular structure is you have a 6 carbon, and because we only have a 12H, so those kind of molecular has one degree of unsaturation, which means it can have a double bond or have a cyclic structure like this. So both of them has C6H12, right? So then if you have a double bond, you cannot have a cyclic structure, because otherwise you will not have this much H. Right? Now this open chain structure again, it looks like a rod. Now this second structure is cyclic, and cyclic, that means you have like a hexagon ring like this, cyclohexane, and cyclohexane, and then you will see this. So this you probably difficult to imagine to understand or imagine, and the second molecule of this cyclohexane will have a larger contact surface area, like you have 2 pair. And so then the first one that the hexane like have one double bond, and all the 6 carbon not a cyclic structure, again kind of like a rod. Even though rod has more contact surface area than 2 balls, but you can imagine it has less surface area than your two hand. Right? So these 2 molecules in terms of dispersion force, and that depend on 2 variables, depend on the size or depend on the molar mass, then that is the same. The second variable is the shape. Shape, you think about which one has more surface or contact area, and this one has more contact area. So therefore, after we compare these 2 variables, and we come up with a conclusion, this second molecule has a stronger dispersion force. Now you want to compare the boiling point. Now you come up with conclusion, this one has a stronger dispersion force, but you want to make sure you're right about the result of boiling point. You have to examine whether you have some other force or not. Now again, all the other 3 forces, except the dispersion force, require those molecules or those particles, molecules, every atom will not have the polar atom, so those molecules must be polar. And as we start in chapter 10 again, this compound has C to H bond, and C to H bond, C to C bond, so both of them have no polar bond. If your molecule don't have any polar bond, either because of there is no difference between the electronegativity or no difference between the lone pair distribution of electrons, so there are no polar bond, and no polar bond for sure for any shape, any geometry for the molecular, your molecule is nonpolar. So if nonpolar, then the only force for both of these 2 types of material is the dispersion force. And we already know this one has a higher or stronger dispersion force, so therefore this one will have a higher boiling point. Alright, so let's go on to study the second, little bit stronger intermolecular forces called the dipole-dipole attractions. And I highlight this word polymolecular, which means even though relative strength per gram of material is stronger than the dispersion force, but it has more restricted requirements. It's only for those polar molecular, which means those molecules have a permanent dipole. So because of the bond polarity and the shape, and so those molecules will have a dipole moment, and so dipole moment, it could be one good criterion or index people can use to decide whether your molecule is polar or non-polar, but we don't have those kind of number like what we use for the bond polarity. We can simply use the electronegativity difference and to see whether your bond is polar or non-polar. And so then you can also like measure the dipole moments for the molecular. And I did not see any people come up with a scale or number at the cutting line, how much dipole moment is for the polar molecular, how much is for non-polar molecular. We don't have those numbers. But you will see that those dipole moment numbers, as the molecule become more and more polar, the dipole moment become larger and larger. But even for those we usually so-called non-polar molecular, you probably also see this number that is not really zero, right? So that is about the polar molecular, and the permanent dipole, it will add on to the dispersion force we talk about, because dispersion force is for every type of material. If you have the permanent dipole in the molecular, then your molecules not only have the dispersion force, it can only have the dipole-dipole attractions. And so therefore it's reaching the boiling point and melting point relatively to those non-polar molecules of similar size and shape. And here this picture tells you what happened, what is like the ultimate reason for the dipole-dipole attraction. Because in those polar molecules, you have a permanent dipole, which means one side or one point in the molecule that is relatively negative, the other point is relatively positive. And then similarly for this molecule, so these two similar molecules, both of them are polar, then this relatively negative point from one molecule, it will attracting to the positive point from another molecule. And this attraction indicated by this dotted line is the so-called dipole-dipole attraction. In terms of relative strength, which means the strength per gram or per kilogram per pound, it is stronger than the dispersion force. Right? And you can see this dramatic influence, the dramatic change of those physical quantity we talk about here, boiling point and melting point, because of the dipole-dipole attractions. And as we talk about Tuesday, so those polar molecular has those polar bond, and then those polar bond also dramatically change the molecular's chemical reactions. And you can see, compare these two molecules, one is formaldehyde, the other one is ethane, and both of them has the molar mass is about 30.03. So therefore, for each one molecular, so they have a similar mass, and then we can compare. That means you will compare them as like per gram or per like 30 grams. And then they have different chemical formulas, molecular formulas, because they are different compounds. The formaldehyde is C820, the ethane is C2H6, and the loose structure for the formaldehyde is carbon, single bond to 2H, and double bond to oxygen. And then for ethane, you have carbon single bond, and then each carbon bond, you use single bond bonding to 3H. So then we study those kind of compounds carbons, they don't have any polar bond, it's non-polar molecular, but this molecule has carbon to oxygen double bond, and then we know this center carbon, or this molecule is only one center, has a molecular geometry trigonoplanar, and then this trigonoplanar, even though that's so-called non-polar geometry, but as we said, for those non-polar geometry, your molecule can end up like polar, depending on what are the bonds. So in this case, we have one polar bond and two non-polar bonds, so therefore we have different polar bond, and different polar bond for those non-polar molecular structure is also a polar molecular. So therefore this is the polar molecular. For the polar molecular, we will have the dispersion force, and we will also have the dipole-dipole force. Okay? Now the dispersion force depends on the shape and depends on the molar mass. So roughly these two molecules have the similar shape. The molar mass is also the same. So therefore they have the same strength of dispersion force, and so then we can see the boiling point is dramatically different. The boiling point for this formaldehyde is about -19.5, for the ethane -88. So the formaldehyde, the boiling point is much higher than the boiling point of ethane, and we know boiling point is directly proportional to the intermolecular forces. If your boiling point higher, which means you have a stronger intermolecular forces, then we already come up with a conclusion. Both of them have the same strength of the first type, the dispersion force, and so then you are looking for some other force, other type of intermolecular forces, and that is the dipole-dipole force for the formaldehyde, right? So that is a good example that we can see the dipole-dipole force really can influence the intermolecular forces if the molecule is permanent polar. Right, now this table compare more compound, and you can see this vertical axis is the boiling point for those different compounds, and this horizontal axis is the dipole moment. So gradually going from this left to the right, these 5 different compounds, their dipole moment getting larger and larger. That means they become more and more polar as a result. And well, we can see the result is the boiling point for these 5 compounds is getting higher and higher boiling point. Right? So then you can see the reason for that is the intermolecular forces getting stronger and stronger. Right? So we know every compound has the dispersion force. The dispersion force depends on 2 factors, depend on the molar mass, depend on the shape. And we choose these 5 different compounds. We can see these 5 different compounds pretty much has roughly the same molar mass, all of them in between 41 and 45. 41 and 46, so something like that. So, but roughly they have the same molar mass. The shape is about the similar, so some of them is more like spherical, and some of them is more rod, but not dramatically different between their shape. Right? So considering that 2 factors, similar molar mass, similar shape, so the first type, dispersion force for all the 5 compounds are the same. If all of them don't have any other forces, all the 5 should have roughly the same boiling point. But the data show you, or the results from experiment is show you the boiling point for these 5 compounds increasing in this pattern, and that means there are some other forces. Then you can see those other forces that come from the dipole-dipole attractions. The first one is the propane, which is non-polar molecular according to our criteria, even though the number here for the dipole moment is not really 0. Right? So then this one become slightly more polar because you have that O bonding to 2 carbon, and that 2 carbon is not linearly bonding to the O. Is kind of for the O, for this middle O, is a band structure. So the polar bond does not come out, so the molecule is polar. And similar, examination, for this one. So this one also polar and this one is polar. So all the other is really polar molecular, even though they have some other parts, they have more than one center. As we talked about, you have one center that is polar, and if you don't have too much non-polar center, your molecule is polar. But so that is another example that tells us the dipole-dipole attraction really influence the intermolecular forces and on, and makes the intermolecular forces become stronger. As a result, your boiling point getting higher. Right. So now this example is about which of those these following three molecules have dipole-dipole forces. Right. So now we know to have dipole-dipole forces, your molecule must be a polar molecule. Must be polar. So then we learn in Chapter 10 to decide whether your molecule is polar or non-polar by examining their chemical bond, by examining their geometry, their shape. To examine the geometry or the chemical bond, and you need to draw the loose structure. So for the first one, you have CO2, and then you will see the loose structure. For CO2, you will start with first get the so-called the skeletal structure. Identify carbon is the central atom, and then two oxygen are the terminal atom. And then you counting together, you will see there are 16 valence electrons. So then you will distribute this 16 by first to put one pair between the center and terminal atom. And then you complete the octet for the terminal. And then you counting how many electrons left over before you finish the last atom. And so then in this structure right now, you already have 16 valence electrons. So then you have 16 available, 16 used, so therefore you have 0 left over valence electron. If you have left over, you will put them as a pair on the central atom. But now we don't have any left over. So then what you do, whether you have left over put on the central atom or you don't, you still want to double check that at least it has octet if the central atom needs octet. For most of the central atom, it needs octet. A few exceptions that don't need octet, like beryllium, boron, aluminum, and those smaller atoms. Carbon is not the usual exception, and so what you do, you are going to take away some of those electrons that you assign to the sides. So I will take these two away, and also take these two away, and then I will share that in between the oxygen atom, the carbon atom. Right. So then this is the loose structure. This is the best loose structure, and then we know this molecular geometry is linear. Okay. Now linear molecular geometry are the so-called non-polar molecular geometry. For those kind of non-polar molecular geometry, unless we have a different polar bond, otherwise we will have a non-polar molecule. But in this example, we don't have a different polar bond, even though we have a polar bond. Okay? So we know the bond between carbon and O, even though it's double or triple or single, we know that will be polar. And similarly between the other O, this carbon, so we have two polar bond between carbon and O, but they are the same. Okay? So this CO2 molecular is non-polar. Okay, let me change the 10 color. So this is non-polar. Non-polar. But non-polar molecular do not have other forces except the dispersion force. So non-polar molecule will not have the dipole-dipole attraction, not have the hydrogen bonding. It cannot give you the ion dipole attractions. Right. So then similarly, we will examine the B, the second molecule, which has the molecular formula CH2Cl2. As we said before, you want to decide what kind of force you have. You have to know the molecular structure, the molecular geometry, and what kind of bond you have in the molecule. Right? So you will start with, to answer both questions, you will start with raw root structure. And we know the carbon is the only center, so we have 2H and 2Cl. And so that is our that's will be our layout of the skeletal structure. Right. So once you have those ideas, you count out total number of valence. So we have one carbon give us 4, and we have a 2H that will give us 2. We have 2Cl that give us 14. So therefore, altogether you have 20. You have 20 valence electron. So then when you distribute, you first distribute one pair. We use a line representing one pair between the center and the terminal. Center, terminal. Center, terminal. Center, terminal. Right. So then the next step, you will try to finish or try to complete the octet for the terminal atom if they need octet. H don't need octet. So therefore we move on to chlorine. To complete the octet for one chlorine, you're adding on 3 more pairs. And then you do the same for the other chlorine, adding on 3 more pairs. Right? So now we have complete all the terminal, except the last atom, that is the center. So then you will take a break and calculate how many electrons you already have right now on the structure before you check the last one yet, whether the last one needs octet or have octet already. So therefore you will take a break and calculate how many electrons right now on the atom, on the structure. There's 8 here. 8 here. 1, 2, 3, 4 pairs. And 8 here. 1, 2, 3, 4 pairs. That gives us 16. And 2 here. 18. 2 here. 20. So therefore, right now the structure already have 20 electrons, 20 valence electrons. 0 left over. If you have left over, you put on the center. If you don't have 0 left over, you still want to check. This center atom, does it need octet? Or do it have octet? So this one has octet. It needs octet, it already has octet. Right, so therefore we finish the Lewis structure, and for this one that will also be the best. For some other atom, if the center atom is sulfur and phosphorus, you probably want to use double bond, even though it's already have octet. You can make it has like 10 electron or 5 pairs instead of 4 pairs to make the formal charge better, smaller. Right, but for this one, that's it. So you have this Lewis structure, then from this Lewis structure, we can see this central atom has 1, 2, 3, 4 electron groupers. So therefore, the electron geometry is tetrahedral, and then we don't have any lone pairs. If you don't have any lone pair, your molecular geometry is the same as electron geometry. So the molecular geometry is also tetrahedral. Now, tetrahedral and linear. So this is tetrahedral. Now tetrahedral or linear. So that's 5 basic geometry plus 1 modified. That's spiral planar. So altogether 6 of those geometry called non-polar geometry. So for those kind of geometry, unless your molecule have different polar bond, your molecule will be not polar, even though you have polar bond. If your polar bond is the same, then your molecule will be non-polar. Now, this two is a very good example. So that is linear, and this is tetrahedra. So both of them belong to the same type of geometry. We call them non-polar geometry. But that one don't have different polar bond. It have a polar bond, but all the polar bonds are the same. Now this one have a different polar bond, a different bond. The CLC is polar, but H2C is non-polar. So when you have those kind of non-polar geometries, so even though the name non-polar geometry, but if your molecule have the polar bond, that non-polar bond, that means we have a different polar bond, and your molecule will be polar. Right? So this second molecule, this CH2Cl2, and we come up with a result that is a polar molecule. So if it's a polar molecule, which means it will have a dipole-dipole attraction. It also have a dispersion force, but in addition to those will add on. In addition, this will add on. In addition to that, and if you have all the others, they can also add on. If you have that, that will add on to this dispersion force and make that stronger, make your intermolecular force become stronger. But this question asks which one has dipole-dipole force. Okay, now we know A don't have because A is non-polar. Now B we know is polar, so therefore B have. B has. So the last one is methane. Methane is CH4. So you have a CH4, and C is central atom. So therefore C and H and H and H and H like that. And so then you count in the total number of valence electrons, you have 8. And distribute like that. And then you try to complete the octet if they need, and H don't need octet, so therefore all the terminal H already finished the sort of octet. And then you are checking the last atom, before you do the last atom, you're checking the electron, how much available, 8, how much used, 1, 2, 3, 4, 4 pair used. So 0 left over. And then you still want to see this carbon has octet, if carbon need octet. So perfect, that's our final result for the loose structure. Then once we have the loose structure, we can decide, or we can determine what is his electron geometry and what is his molecular geometry by counting how many electron groupers. So this is only central atom, and there's 4 electron groupers because there's 4 atoms bonding to 8, and there's no lone pairs, 0 lone pairs. So you just adding how many atoms bonding to the center, and how many lone pairs altogether is called the electron groupers. So we have 4 atoms bonding to 8, and we have 0 lone pairs. So therefore, we only have 4 electron groupers. 4 electron groupers will give you the electron geometry tetrahedra, molecular geometry, depending on whether you have lone pair or don't have a lone pair. If you don't have a lone pair, so these two are the same. Right? So your molecular geometry also tetrahedra, and then tetrahedra, as we talk about for this second problem, for problem B, is the sort of non-polar geometry. For tetrahedral geometry, for linear geometry, for the trigonal planar geometry, for the trigonal bipyramidal, for the octahedral, or for the square planar geometry, those are the 6 non-polar geometry. If you don't have a different polar bond, your molecule is non-polar. Now this is CH, the only bond we have, so all of them are the same and all of them are non-polar. Even though, in addition to the same, they are also non-polar. So definitely this methane is non-polar. So I will say this is non-polar. Right? So only one that is polar is this. So therefore, this is the only one that has the dipole-dipole force. Right? So this is about this example. Now let's see this CRE. So you will do the CRE on your scantron, on the back side, so you will start on the number 51. So this asks you the question, which of those molecules have dipole forces? So again, have dipole force molecule must be polar. And how you identify your molecule polar, non-polar? You just follow on the last slide. So what we did is draw the Lewis structure, and first decide what is the molecular geometry, and also from Lewis structure decide what kind of chemical bond we have. And if we have the polar bond, and we have those kind of like polar geometry, and then we know it's polar, and so on. Okay. So for this three compound, and let's say the first one is Ci4. So let me change the color back to the one that we used to have. So that means C is center, and then we have I, and I. Right? So this will be our skeletal structure for this Ci4. And then you're counting the total number of valence electrons. So you have 4 from carbon, and then you have 4 times 7 from 4 iodine. Altogether, we have 32 valence electron. Right? So then you will distribute that 32 by first put a pair between the central and terminal. Then you finish the octet for all the terminal first. Any 3 more pairs. For each one terminal. Right? So now you finish all the terminal. You select now the last central atom, the only central atom. Then you take a break and see how much available, how much you use. Okay? So you have 32 available. Okay? Now right now you have 32 used. So therefore you have 0 left over. Okay? If you have left over, put on the center. If you don't have left over, you don't put on the center. But either way, you have to check if the sample needs octet. If we don't need octet, so if you don't have octet, use double bond, triple bond. Okay? And for this problem, the center atom carbon needs octet. And also for this structure so far, it already have 4 pair come from these 4 single bond. So therefore, it has octet. And then that's pretty much the best loose structure for carbon. Okay? It just needs octet. Right, so this structure, and then we know the Mg, and probably you want to see like Mg and Eg first, Eg and Mg. Eg depends on the electron groupers, depends on how many, if like 2 is linear, 3 trigonal planar, and 4 is tetrahedral, 5 trigonal biperimeter, 6 octahedral. So now it's 4 that means tetrahedral. And then we also have one pattern. If you don't have any, if you have 0 lone pair, no lone pair, the molecular geometry, electron geometry are the same. Right? So both of these two geometry are tetrahedral. So even though usually we worry about in this class what is the molecular geometry. Right, so molecular geometry is tetrahedral, and is non-polar geometry. For non-polar geometry, unless we have a different polar bond, otherwise our molecular is non-polar. Okay? Now in this Lewis structure, I tell you we have only one type of chemical bond in this compound. Is the chemical bond is between C and I. Okay, so therefore, even no matter they are polar non-polar, they are the same. And you can see if you use the electronegativity, so you will see this carbon and I, they probably have the same electronegativity. But because of this lone pair, on I. So the bond between carbon and I is also polar. But we have all the bonds are the same polar. So therefore, for those kind of non-polar geometry, if all the chemical bonds are the same polar, it cancels out. So make this non-polar. Okay? So the first one is non-polar. If it's non-polar, that means no dipole-dipole attractions. Right. So let me erase this. Okay. Just say this is non-polar, thus no dipole force. Right, now let's examine the second one. So this is for the first one. The second one is CH3Cl. So again, you can start with draw the root structure. Okay, so you have a 1C, so that will be the central atom, and then you have a 3H, and then you have 1Cl. Right? So this is our skeletal structure. And very important, you have to draw the root structure and see what kind of chemical bond you have, okay? And what are the molecular geometry for these last two chapters. Okay? Now you're counting the total number of valence electrons. Okay, so 1 carbon give you 4, 3H give you 3, and then 1Cl give you 7. So altogether we have 14. So what do you do? No matter the Cl, no matter the H, what else, you just draw like a 1 dash between the center and terminal. Center, terminal, center, terminal, center, terminal. Okay? So once you have that, you just continue. You can continue. You don't take a break or do without bond until you have the last, come up with the last atom. Right. So then the next step, you are going to complete the octet for the terminal if they need. Try to see if they need. Okay? Remember there are a few exceptions. H don't need. Okay? So the only terminal atom in this example that needs the octet is Cl. So what you do, you just want to give them octet if they need. Just adding like 3 more pairs, because you already have 1 pair from that dash. Now it has octet. Okay? Right. So then we already finished the so-called octet for all the terminal. The only atom you did not check yet is the carbon. So leave the last atom, then take the break. Okay? So here, let me use like this pair is 8. Okay? On this side is 8. Because 1 pair, 2 pair, 3 pair, 4 pair is 8. Okay? 8, 10, and 12, and 14. So now on this structure, you have 14 valence electrons, and that means you already used that much, and it's 14 available. So therefore 0 left over. Okay? But it's usually that's okay for carbon. So the carbon already has like 4 pairs, and you don't have left over, so therefore you don't do anything else, and it has octet. Right. So then similar as for the first molecular, so our Eg and our Mg, we can say both are tetrahedral. Okay? So tetrahedral molecular geometry are non-polar geometry. Okay? Unless, for those non-polar geometry, for all those 6 non-polar geometry, unless in the molecular we have a different polar bond, okay? And if we have a different polar bond, the molecular will be polar, even though the name says non-polar geometry. But if you don't have a different polar bond, then they will become really non-polar. Okay? Now for this problem, we have a carbon to Cl bond. Use electronegativity, use long pair. You will see the bond between C and chlorine is polar. Then between C and H, both of them don't have any long pair. And both of these carbons electronegativity 2.4, 2.1. So therefore, the carbon H bond, carbon hydrogen bond is a chemical bond, covalent bond, is non-polar. So in this 4 bond here, we have 3 CH bond, 1 CCl bond, only one of that is polar. So therefore we have a different polar bond. Okay? Now the result is, so this is the polar molecule. So now let me erase that. So we'll do a similar circle for the second one. So now the second one, I'll use a different color. So this is polar. Polar means it has the dipole force. So this referring to this our second molecule. All right. Right. So we continue to examine the last one, and let's see the last one is relatively simple because the last one is HCl. And you can still draw the new structure, but we don't have some of those names for those, like the electron geometry and hybridizations. So you just see like this is the layout of the two atoms. No matter what two atoms you have, there's only possibility for them. You know, the skeletal structure. Then you will see the total number of valence electrons, 1 from H plus 7 from Cl, so you have 8. And then you just, again, you want to make a molecule, that means you have to connect them together, connecting all the atoms together. And then you will see they need octet, H don't need, and only Cl need octet. And then that's it, they already all have 80 electrons. Okay? So that tells you this molecule has only 1 chemical bond in it, is between H and Cl. For those kind of molecules, if there's only 1 chemical bond, okay, and that chemical bond maybe single, or maybe double, or maybe triple, so no matter what they have, and obviously this, you can see the molecular geometry of for these two atoms, it's just one line, you can call that linear, but not really those kind of linear, you have 3 atoms. So then the bottom line is that for those kind of molecules, only have 1 pair of atoms, and then your molecular polarity is very simple. If this bond between this pair of atoms, between that 2 atoms, is polar, maybe because of electronegativity difference or because of those long pairs, and then your molecule become polar because there's only 1 bond there. Usually, the problem becomes very, very complicated because there's a lot of chemical bond in the molecule, like in those kind of molecular 4 chemical bond, and lot of molecules have more chemical bond. And those bonds is polar or non-polar or different polar, and they might cancel out or not cancel out. 1 bond cannot cancel out of itself, so there is no other one to counteracting with this one. So therefore, if this bond is polar, your molecule is polar. Okay? So let me do the same and erase those. So we know this molecule is a polar, because there's only 1 bond. Again, there's only one bond here, and 1 bond is polar, then your molecule is polar. Okay? So let's say this is polar. Okay, for the polar molecule, you can see therefore has dipole attraction, dipole forces. So I will circle this for the last molecule, for the last compound. Alright, so that means for the first one you don't have dipole. For the second one you have dipole, and for the last one you have dipole. Right, now let's go on to talk about this number 3, the hydrogen bonding. Hydrogen bonding is relatively stronger, not the strongest intermolecular forces, but it's stronger than the first 2 types, relatively, again, per grams. But it's very, very selective. That means when a very electronegative atom is bonded, and this bonded means really those chemical bond or covalent bond. covalent bond is really chemical bond. And so then this very electronegative atom, fluorine, the En electronegativity is 4.0 and 3.0 and 3.5. So those are really electronegative. So they are so electronegative, they will pull the bonding electron towards them. So most of these two electrons is on the fluorine, most of this is on the nitrogen, and most of that is on the oxygen. And that's pretty much leave this H naked, become like exposing the H proton. So therefore this side becomes so positive, it can attracting the electron cloud from the neighboring molecules. And that kind of attraction, it still belongs to those dipole-dipole attractions, but it's become so special because they only exist for these three type of structures, for these three type of structure. And so therefore we give them a special name, call them hydrogen bonding. So now, you know, like we made some bond here for the O, and we made two more bonds for the N, because usually the O will have like two chemical bonds. You can only emphasize as long as two of the oxygen chemical bond, one of them is bonding to H, that's enough. If both of them bonding to H, that's good. That means more than enough for the hydrogen bonding criterion. And similar for this N. If you have one, you can have three chemical bonds for N. If only one of them, that's enough. If you have all the three, that's good. Fluorine usually have one chemical bond, so that's only structures, right? So this picture tells you the reason for the hydrogen bonding. So you can think about those negative will become relatively larger than some other permanent dipoles. So therefore this positive also relatively more positive, even though really not like one positive or one negative like those chloride ion in the table salt or the sodium ion in the table salt, not really one unit charge yet, but it's become much higher. And therefore, this attraction between this negative, this plus, is relatively stronger than the usual dipoles. And you can see those kind of picture, if you review, is also similar for the dipole attractions, but here, those magnitudes, plus, negative, become relatively larger or higher. So therefore, their strengths become higher. And so therefore, we give them a special name for the H bonding. And you can have H bonding, for example, here is between water molecules. This is one H2O, this is another H2O, this is another H2O. So those hydrogen bonding, not chemical bonds. So we use the dotted line representing those stronger attraction called H bonds. Okay? Don't be confused by that. It's not a chemical bond. It's relatively selective only for these three types of material. And so this is one possibility between different water molecules. And obviously you don't have to limit between water and water. You can have between water and ammonia. Obviously that is similar between ammonia and ammonia, is similar as between water and water. You can have those mixtures. You can have water and ammonia, or water and ammonia, or water and HF, and ammonia and HF. So as long as you have like those three structures in H, and then they will produce the hydrogen bondings. Okay. So hydrogen bonds are very strong intermolecular attractive forces, stronger than dipole relatively again, or dispersion force. So substances that can hydrogen bond will have a higher bonding point and a melting point than similar substances that don't have. Okay? But hydrogen bonds are not nearly as strong as a chemical bond. So again, this word is really not a chemical bond, because you can see the result is about 2 to 5% of the strength of the weakest covalent bond. So the covalent bond is much stronger than this so-called hydrogen bond. Now you can also see the effects of the hydrogen bonding on the boiling point. Again, we compare these two compounds. Again, these two compounds are called isomer. So these two are the isomers. And as you study more and more chemistry, you will see more and more isomers. Isomer means they have a similar formula, same, C2H6O, C2H6O, same, exactly the same, but different structures, maybe different chemical bond, maybe different spatial arrangement. So as long as something those differences, you cannot change them in the room temperature with thermal energy, and then we call them isomers. So the first one is ethanol, the second one dimethyl ether, and probably from the model you cannot see that very clear. So in terms of root structure, this one will have the C and O and H, two pairs here, and an H here, and another H here, and three more H on this. I draw those H with different angles because I want to run out of space. But pretty much you can decide what are the real geometry for the carbon, and for this O is tetrahedral molecular geometry, and band. And for this dimethyl ether, in similar you have the oxygen, and then you bond into one carbon on one side, and bond into another carbon on the other side, and then each one carbon has 3 H bond to 8, and this has 3 H bond to 8, and this has 3 H bond to 8, and then you have the two pair of non-bonding electrons on the oxygen. So then we know both of them will have the dispersion force, because dispersion force is so general for everything. Then dispersion force will depend on the molar mass, depend on the shape. Molar mass is exactly the same because they have the same molecular formula. Shape is roughly the same because it looks like a rod, even though not a very straight rod. So therefore, dispersion force pretty much the same. You will not give you any difference for the boiling point. But the result, the boiling point of this is much higher than the second one. So then what you can see is compare to other forces. Do we have a dipole? Yes, you have dipole because both of them are polar. So this center is a polar, and we have this center non-polar, this center non-polar. But as we said, we have 3 center and 1 polar center, 2 non-polar center, that's still polar. So this one has a similar 1 polar center. So dipole, both of them are polar, so dipole pretty much is similar. And maybe a little different because dipole moment is different, so that one maybe a little more polar. And that will give it a little higher, stronger intermolecular forces. But I don't think that's a little stronger dipole forces because the more dipole give that much of boiling point difference. So really, there is another force that we should consider to accounting for this larger difference of the boiling point is in this structure, in this ethanol, we do have the O bonding to H, as we said here. But in the second structure, we have the oxygen atom in the structure, but this oxygen atom is not bonding to any of those H, but it's bonding to the carbon, So you don't directly bond into the H, even though you bond into the carbon bonding to H, that's not direct. So that's skipped by one bond, by this bond, or by one atom. So therefore, does not have this kind of structure. Okay, so what really makes the boiling point difference is this one cannot have the hydrogen bonding, or do not. So this dimethyl ether do not have the hydrogen bonding, but ethanol does have the hydrogen bonding. Right? And that's the reason ethanol has a much higher boiling point than the second one. Has H bonding because it has this part in it. just emphasize that part. What is that part? That part is O bound to H. Right. This one, 8 does not have H bonded because no OH in it. Okay? And obviously you don't have N in it, you don't have F in it. Okay? So if you don't have, okay, don't consider that as a molecule, you don't have this part. Okay? If you have O in your formula, not enough. If you don't have O to H bond, you don't have hydrogen bonding. And so the scientists find out those hydrogen bonding is more interesting. I think from those experimental data to find out the hydrogen bonding is like this: 4 group of hydride. So you have that group 4A, carbon, silicon, germanium, and tin. And as you compare their hydride, that means you have that atom from the group of 4A bonding to H, and all of them bonding to 4H. And then the group 5A and bonding to 3H, group 6A bonding to 2H, group 7A bonding to 1H. So what you find out is for the group of 4A, it's pretty much as what we predicted. So they have a similar structure, similar polarities. None of them is very polar, and then so the only force for all these 4 compounds, this dispersion force, you can see that increases with smaller mass. So all of them have 4H. The only difference making them have a different molar mass is the central atom. So carbon is lighter, smaller than silicon. Silicon is smaller than germanium. So in terms, so therefore, as we expected, the only force for these 4 compounds is dispersion force. And the dispersion force increases because the molar mass increases, so therefore the bonding point increases. You can see the other pattern, you do the other way. So when the molar mass is getting smaller, so your bonding point is getting, your dispersion force is getting weaker, than your bonding point is getting lower. Okay. Now that's not the same pattern. Even for 3 of them is the same, but not all the pattern for all the 4 compounds. For the other 3 groupers, for example, for that group 6A, and we have that central atom, maybe oxygen, maybe sulfur, Se and Te. Again, as expected, if you don't have those hydrogen bonding or the dipole forces, so as your molar mass is getting like smaller and smaller, your dispersion force is getting weaker and weaker, your bonding points are getting lower and lower. But boom, suddenly water has so small molar mass, it's about 18, and the boiling point becomes so high. So where the higher boiling point for water come from? And that's one of the good result that make us think about in water and HF and ammonia, those kind of structure. We have a spectrum for intermolecular force called hydrogen bonding. So then the next type is ion dipole attraction. So this will be the last type of intermolecular forces, and this is the strongest one. And so then the requirement is in a mixture of ion from an ionic compound, okay, that attracted to dipole of a polar molecule. Okay, so again, the requirement for this last strongest intermolecular forces is between ions and polar molecules. And so now we summarize, as we see in this table, those intermolecular forces. These dispersion forces are the relatively weakest intermolecular forces, which means per mass. When you have a per mass per gram, compare 1 gram by 1 gram, that is the weakest. But it's very general. It appears present in all the molecules and atoms. And so now we know we have two variables influence the magnitude. One is the molar mass, the other one is the contact area, contact point, or the shape. And the second type is dipole-dipole, those for the polar molecular, and that become relatively stronger compared with dispersion force. And then we go on to the type 3, hydrogen bonding. Hydrogen bonding again is not really a chemical bond. The requirement for the hydrogen bonding, so that's the number 3, is you have the H directly chemical bond, so there is a chemical bond, to either O, N, or F. So then the strongest one is ion dipole attraction, and that requires you have those that ion, and also have the polar molecules. So ion dipole attraction are the strongest intermolecular forces. Ion dipole attraction are essentially important in the aqueous solution of ionic compound, and that is about the summary of the intermolecular forces. And this table is very similar to what I draw here, and you can number also here. So that is the first one we talk about. Even those numbers really not that meaningful, but just give you some idea. We have 4 different forces. Right. So now let's see this example is one of these compound is a liquid at room temperature. Which one and why? Which one and why? I think that imply so one of them is liquid and all the others is not solid, is gas. Which means all the other has relatively weaker intermolecular forces. So the problem, this quiz, the question asked you is pretty much ask you to identify which one of these 3 has the strongest intermolecular forces. So which one has the strongest intermolecular force or forces? I, M, F. I, M, F. Right. So to answer to the question, you have to examine all these 4 different types of IMF. The first one, no question, so all of them has a dispersion force. Okay? And so then you compare which one is more, which one is less. I think if you calculate the molar mass, pretty much all of them are similar, because all of them has 2 heavier atoms, maybe 2 oxygen, or maybe 1 carbon, 1 fluorine, or maybe 1 carbon, 1 oxygen. And so that pretty much means they all have the similar strength of dispersion force. And then let's see, do they have the second one, dipole-dipole? Yes, all of them are polar. Okay? This one is polar, because this part is band, that part is band. And this is tetrahedra, but there's not all the chemical bonds the same, so only one bond polar. So that is a polar molecular. That one we saw before is a polar molecular because the geometry for the only center, molecular geometry for the only center is the trigonal planar, and the trigonal planar is very similar to the tetrahedra, but if you have different polar bond, that it becomes polar. Okay? So all of them are polar, so therefore all of them have dipole-dipole. So you don't have you will not make any difference. It's the same dispersion force, same dipole-dipole force, and then we'll go on and see if we can make a difference, use some other force. So we'll go on to see which one has hydrogen bonding. Okay? Well, hydrogen bonding, that means you want to have an oxygen bonding to O. Okay? So that is good for the H bonding. Okay? And this is also good for the H bonding. But this, no. And this, no. Because you have to say that like this. So O bond to H. O bonding to H. You have F, but F is not directly bonding to H. So that's not good. You have O, but O is not directly bonding to H, it's bonding to C. Right? So that means this, the only one has the H bonding. Right? And so then the previous two forces, they all have the similar, because they have the similar model mass, similar shape, and similar dipole. And the only one that makes them different is this one, hydrogen bonding. Right? So the last one, the hydrogen peroxide, is the one that is liquid at room temperature, and all the other two is gas, which means their boiling point is lower than the room temperature, or lower than the hydrogen peroxide. Right? Properties similar. So this question asks you which one is the liquid at room temperature, and the others is gas. So this is good that tell you all the others is gas, not solid, because otherwise you will see that does not make sense. Okay? And so then similar reasoning, just compare all the forces. They all have the disappearing force. Then you'll see which one has more disappearing force. But that depends on the molar mass. If they have pretty much similar molar mass, same disappearing force. Okay? So the first pair, same disappearing force. Okay? And then like dipole, they also both of them polar. You check that both of them polar, and so then therefore both of them have dipole attractions. Right? So then we don't have a break. We'll see which one has more forces. So the first one is methanol, so that has this kind of structures. I mean the loose structure. Right. So then the other one has this structure. Right. So you can see that this one has O bonding to H, and that one have the hydrogen bonding. And this one have F, but F is not bonding to H. Okay? So that is the one that will make the difference. So the hydrogen bonding make that type of compound has relatively stronger intermolecular forces. Stronger intermolecular forces will give a higher boiling point, which means it is liquid, not boiled yet, at room temperature. Right? So this will be the one that is liquid. Now similar for the second pair. For the second pair, if you do an expansion, so this O is bonding to C, and bonding to C, bonding to C, and then you have these two lone pairs, and then this carbon has 3H, and this carbon has 2H, and this carbon has 3 more H. Right. So then from this structure, and you will see in details what are the chemical bonds. Okay. And so then similar for this, you have a 3 carbon, and then you have 1 N. You draw the structure like this. So this C3 means you have this 3H. Now this C2 means you have this 2H. I shall draw on top, but I don't have space. Now this 2H here have 2H like this. And this 2H here means you have 2H like this. Then you have lone pair here. Right? So now, from those structures, we know this molecular geometry for this carbon tetrahedra, and for this O is bound tetrahedra, and tetrahedra, and this is trigonal pyramid molecular structure for this N. And then you will see this center is a polar, or the other center non-polar, but they won't have 3 non-polar. So this pretty much makes this molecule still polar. Okay. And similar for this, 3 center nonpolar, 1, 2, 3 center nonpolar, and the center polar. So this molecule is polar. So then both of them are polar. And both of them have a similar molar mass. So again, these first two types intermolecular forces are the same. What makes the difference is this molecule have the N bound to H, and that means has H bonding. H bonding is this type. Both of them have that. Only the second one have this. So therefore there's extra forces for the second one. So therefore this will have a stronger intermolecular forces, which means has a relatively higher boiling point. Right? So that is about how we compare those. Now this CRE is about what is the strongest type of intermolecular force present in H2, in this one particular type of compound called H2. H2 loses structure is very simple, so that's it. You have two H atoms, one chemical bond, and no lone pairs, no really complex structure, right? So we don't have a dipole, we don't have a polar molecule. We don't have all the other three forces. The only force we have is the dispersion force. And the average dispersion force is the only intermolecular force, so therefore the only intermolecular force becomes the strongest. So dispersion force is the strongest force that is in the H2. And then for this one, you want to see what is your strongest type of intermolecular forces. And C is the center, H, and 3 fluorine. So you have this. And now you know that total number of valence electrons is 4 plus 1 plus 21, and that gives you 26. Complete octet. And this is 26. Okay, so therefore you don't have any lone pair electrons or any dot on the carbon, only 4 atoms, means 4 group of electrons. So electron dominant tetrahedra, molecule dominant tetrahedra. Tetrahedra, even though it's so-called non-polar geometry again, but if you have a different polar bond, that is also polar. And we have a different polar bond. Well, this bond is polar, this bond is polar, this bond is polar. Boom, this is non-polar. So that means we have different polar bond. For those tetrahedral geometry and trigonal pendant geometry, linear, and those non-polar geometry, if you have different polar bond, then it's polar. Alright. So then we have this one, because that one is for everyone. We also have this one. Do we have this? To have the hydrogen bonding, you have to have the F bound to H, O bound to H, N bound to H. Now in this molecule, you have the F, you have the H, but they are not connected directly. So there is an atom in between. So for this molecule, we can see this one, no. This one, no. And so then what else do we have? Do we have an ion dipole? No, we don't have ion. Okay, so we have dispersion. We have a dipole. Then we know dipole is relatively stronger, especially for the same molecule, than the dispersion force. Right, so the dipole is the strongest for this molecule. Right, now let's continue to see what is the strongest one for this one, polar reciprocal pattern, right? This type of structure, you have to be able to do a expanding. Right? So this close combine the molecular formulas. So what this means, you have N, H2, that means bonding to 2H, bonding to 2H. And this N is bonding to C. And this C on the right, you can put on the left on the middle, bonding to 3H. And that is one lone pair on this N that will make it octet. Okay. Alright, so then you see this kind of results. So this type of here, this molecular geometry is trigonopyramid because you have four pair of four electron groupers. So therefore, electron geometry is tetrahedra, but the one long pair. Therefore, molecular geometry is different than the tetrahedra. It becomes a trigonal pyramid. And here you have like zero long pair, and you have the electron geometry or the electron group is 4. Electron geometry is tetrahedra, molecular geometry is tetrahedra. So this part, and so you can see this tetrahedra, that is also a trigonal pyramid, and this molecular is polar because you have that the N, the bond between N and C is polar, and between N is polar. And you can see like both sides are polar, and they will not kind of odd because they have different geometries. Alright, so what do we say? We have this pattern because that's for everyone. Dipole, that's for this kind of polar molecular. So then we will say, do we have some even stronger one? Do we have the hydrogen bonding? Well, we have the H bonding to N. That's perfect. That means we have a hydrogen bonding. Okay? Alright, so therefore, we have this one, we have this one, we have this one, know this one. Then, if we have all the three, then you know which one is stronger for the same molecule. The hydrogen bonding is the stronger one. Okay. Alright. This slide is about the least, the following molecule in the order of increasing bonding point. So what you do is identify which one has the strongest intermolecular forces. You can do the outside, which one has the weakest intermolecular forces. Let's see, probably pick out the one that has strongest intermolecular forces. Okay? Which one has? Do they have dispersion force? Yes, they all have dispersion force. Do they have a dipole? Yes, they have this. Yeah, that's polar and this polar. They have dipole. Which one have the hydrogen bonding? Well, hydrogen bonding. So those is one type of structure called the line structure. You have to be able to like expanding. So this means you have O bound to C, and bound to 3H. This C and C and 3H. And that's similar here. So you have each of these is a C. So the ending point or the corner are the C. And so now you just finish all those bonds for C because they need 4 chemical bonds. And this will be 3 more H. And this also C, this also C, this also C, also C. So you have C, C, O, C, and C, and like this. Alright, so then you can see all of them obviously have dispersion force. Now which one have the dipole? You can see pretty much. So they are all polar. So this center obviously is polar, and this center is polar. So all of them have polar. So then which one has? So dipole, dispersion force also there. Dipole also there. You can also compare which one has a stronger dispersion by compare which one has larger molar mass. But I think that you can kind of molar mass probably will not make that much difference. But you can see this. So this one, as you compare the dispersion force, this one we have the weakest one because that's the smallest one, and then these two have the same molar mass, same dispersion force. But so obviously dispersion force, that one is the weakest. And dipole, so they are all polar, so I think in that dipole will not make any difference. We can assume all the three have the same dipole force. So dispersion force, these two are the stronger one, and so therefore the highest boiling point will be in between these two. because in between these three, that one has, they all have a similar dipole, that one has the weakest dispersion. Now to break the tie between these two, we were thinking about which one has some other force. So this one you can see clearly have the O bonding to H, so therefore this one has the hydrogen bonding, have -3. And this one don't have the O bonding to H, but have O bonding to C, O bonding to C. Right? So therefore this one will have the highest bonding point, which is N-propanol. Okay? N-propanol, so maybe these two answers. Right? And then we already know both of these two should be higher than that one, so therefore that one not right, and so therefore the answer is this. So that means the lowest bonding point with dimethyl ether, then the next highest one with diethyl ether, then the next one will be the propanol, the highest will be propanol. Make the highest one that propanol has the highest bonding point is because this part of the structure that gives us the hydrogen bonding. Right. So attractive force is also like very important for the general chemical class. Talk about the solubilities. And usually we will see like the sort of rule of thumb, like dissolve like. And you can say that means powder will dissolve in powder, non-powder dissolve in non-powder. And but some molecules were really difficult to tell because they have like they become so large. One part is powder, the other part is non-powder, and then usually we'll use this called the rule of thumb. So like a powder substance dissolving in powder solvents. So the powder solvents usually will have the so-called hydrophilic. Philic means like or love, and hydro means water. OH, CO, CO, COOH, NH2, NH1, and Cls. And then hydrophobic, which means those guys, C2H, C2C. And then many molecules have both of these two parts, have that part, that will I emphasize sometimes. How many signs in the powder, how many signs in non-powders. And so then if they are totally so different, and one is powder, then the other is non-powder, even to have the powder part, and but the powder part were overtaken by the non-powder part. So therefore they become immutable. That means you will see like if they are liquid, you have two layers. So then the powder solvent will dissolve the powder molecule or maybe ionic compound, because those kind of powder dipole attractions, or maybe hydrogen bonding, maybe ion dipole attractions. So that is those kind of powder solvents. Powder solvents typically is water, and some of those smaller alcohol, maybe some of those compounds have those kind of halogen in it. And so there has another example called the methane like chloride. So you have one carbon and two H and two Cl. Okay, powder molecular, again, they were dissolved like in those powder solutes because of those dipole attraction, hydrogen bonding. And non-powder solvents, usually those organic substances like those hexane and or in general alkane, or some of those like carbon tetrachlorides become like liquid at room temperature. So even though they don't have dipole attraction, but the molar mass becomes so large, and this dispersion force become large. And toluene, so those kind of organic non-powder solvents. You can just sometimes use that roughly rule, but like similar dissolving similar, like dissolving like, and choose like those which one is dissolving what. And this problem is choose in between each pair, there are two pair of compound here, which one is more soluble in water. Soluble in water, which means more soluble in water is more like water. Okay? And this one, as you know, called methanol, and this one is, so you can call them 1,1-difluoro, like ethane. It's kind of those halide. So it has two F bonding to carbon, but don't have the F bonding to H directly. Even though this is polar, that is also polar, but this one cannot produce. I mean, that one cannot produce. This one cannot produce hydrogen bonding to itself. Can produce like partly hydrogen bonding to water, but that can produce more hydrogen bonding to water. So therefore, that one is more soluble. So that's similar for these two. So this molecule is simple like pentene, very straight, very simple, not really literally straight. You are zigzag, those carbon, the 5 carbon, but it's non-polar. This is polar. So therefore, this is polar, then non-polar. Both of them don't have other like hydrogen bonding. So this is more soluble, and that is more soluble. Okay, let me see. So that is more soluble because that can have more hydrogen bonding with water, and that means it can be a donor and also donor this H to the O in water can also be an acceptor for the hydrogen bonding because this O can accept the H from water. And this one can only accept but cannot donating the H, so it produces much less hydrogen bond. And then the reason again for this one, this is more polar, just in case you don't see that. So now, what type of intermolecular forces that causes the dissolution of NaCl in water? So that's pretty much think about these 4 type of compound, 4 type of intermolecular forces. And obviously, all between anything can have this pattern. And but to have the dipole, you will have both of them have the permanent dipole. And when you have like that, Na become ion, you cannot think about that as a dipole. So really, the force that causes the dissolving of this kind of ionic compound is ion dipole forces. Okay, so then this is choose the pair of substances that are most likely to form a homogeneous solution. So if I give you kind of problem, you can just use that simple rule, like dissolve like. Okay? So let's examine what kind of force possibly can, what kind of compound they have, what kind of force possibly they can have. So this is ionic and this is metallic, and that is totally different. And this is ionic, this is nonpolar. That's also like too much difference. And this is nonpolar, and this is the polar. So that's also kind of a difference. And this is the nonpolar, and this is the polar. So that's also different. And this is the polar, this is the polar. And both of them can have hydrogen bond, and they can also hydrogen bond between them. So therefore, the last one is more likely to form a homogeneous solution. Okay, and so then this is similar. Let's see the first one. So those are sort of the hydrocarbons, only have a carbon and hydrogen in it. So no matter what they look like, so probably they are all nonpolar. So even though sometimes, even if those molecules are getting so big, and you probably will not see that they dissolve in some of those so small nonpolar organic solvent, but they're not too much different. This is like 10 carbon, that's 6 carbon. So nonpolar, they're very like, similar, they will dissolve very good. And this is ionic, this is nonpolar, that is different. This is nonpolar, so this is ionic, so that's will not dissolve that good. And this is nonpolar, this is polar, they're not good. I think the best choice will be the first one. Right, so now we talk about those different states and how the material will change from one state to another state. One change of states in between liquid and gas. So think about those molecules in the liquid. And even though they have limited freedom, but they still have all those vibrational, rotational, and translational motion. And then we also know that every kinetic energy is proportional to the temperature in Kelvin. So this Kelvin increases, that increases. Okay? And so that's the average. Then we also know different molecule at the same temperature, it will have different this, because otherwise we don't have to see the average. So some of those molecules, it will have a relatively high kinetic energy than others. And what happens is, if those relatively higher molecule have relatively higher kinetic energy on the surface, then what happens, they can break those attraction from the other molecule and get into the gas, gas state. Okay? So therefore, they can vaporize and escape. So then, obviously, that will depend on the surface area. Because if you have a large surface area, and you have a large number of molecules that will be sitting on the surface, then so even though the percentage at a given temperature, how much percent of those molecules will be have high enough energy to go into the gas phase, depend on the temperature, but then obviously depend on the total area. So therefore, you will see if you have those water, for example, you will see if you spread out the water, that will dry up very quick, relatively quicker, because there's more surface area for the vaporizations. And so then the vaporization, like a vapor pressure, what we did in last week's lab, depend on the material, also depend on the temperature. So the temperature, let's say the temperature is proportional to the kinetic energy, is this x-axis, the horizontal axis, and then how much of those molecules, what is the fraction, what is the percentage of the molecule that can get into the gas, or in general, what are the fraction, percentage of those molecules have those kind of kinetic energy, have relatively lower, higher and higher and higher and higher and higher, and then the fraction will become different. So initially, this fraction can less percentage, and then at some point you have the largest percentage, and then as the kinetic energy increases, again the drop again less and less. But if we imagine like there's one cutting line, and that's called the minimum kinetic energy for the escape, for changing those molecules from liquid into gas, and we can draw the line like this starting line. And then for the same material, we have these two blue, we have the blue line, have the red line. The blue line representing lower temperature, the red line representing higher temperature. And then you can see the higher temperature under the red line. Under the red line, there's a larger area. And this larger area representing altogether a larger number of molecules will be able to get into the gas state, which means it will have a higher or faster rate of evaporation. And if you keep the container closed, and it will have a higher vapor pressure, as what we did in the lab. We changed the flask of methanol, has methanol in it, from cold temperature, like ice water, 0 degree to 10, and to 30, to 20, to 20 to 30, then we see the vapor pressure getting higher and higher. If your data is right, you do not have those leakings. And obviously the condensation is those molecules in the gas, they also like constantly moving. So sometimes they will strike the surface of the liquid, and if they don't have like enough kinetic energy, they will be grabbed by those molecules in the liquid, so that's condensed. Or if they don't have enough kinetic energy, sometimes they will gliding together. And then if they moving so slow, once they getting together, they will stop. And that's it. Sometimes you will see some of those droplet of liquid and start together, become liquid. Right. So this process, this process of condensation and that process of vaporization, and it can happen at the same times. So if you keep the container open, and then those vapor molecules will spread out and more. And if you keep the container closed, and then finally those liquid get into the vapor, then the vapor get back into the liquid, and then they can reach in the same rate of transfer. And then you have the so-called dynamic equilibrium. And we'll talk about in the next few slides. But another point I want to say about those phase change is those whether they are endothermic or exothermic. Okay? So the process of changing from liquid to gas called the vaporization is endothermic. And one way to understand that why that is endothermic is you can understand those molecules that are getting into the gas from the liquid, those molecules have a relatively higher kinetic energy. That means they relatively have their own higher temperature. So therefore, when they goes away, and they will take those heat away, take energy away, and so then in order to keep the temperature, so you have to think about those liquids going to absorb heat from the surrounding, and for those kind of process, we call it endothermic. And so then you can measure like what will be the energy required to vaporize like 1 mole of those liquid for different material. That is called a vaporization process. And so then the heat or the energy required, we call that heat of vaporization. And that number should be, as we said, the endothermic, so therefore it's a positive number. Then oppositely, the condensation process, that means initially those molecules in the gas, they have relatively higher kinetic energy. When they get into the liquid, so those extra energy, they were released to the surroundings, so we call them exothermic. So therefore, they will have the negative delta H, and so therefore we have these two, the same magnitude but different sign. And so then this delta H vaporization and all that delta H condensation, they will have the same number but different sign. And also for the same material, it will slightly depend on the temperature. As you can see in this table, for example, for water, this delta H at the boiling point is about 40.7 kilojoules per mole, but at 25 degrees Celsius, it's about 44. You can use those numbers to do the calculation, like calculate the mass you can vaporize, or calculate how much heat you can release or absorb if you want to vaporize or you condense some material. So this problem is about if I have this much of heat, and how much water you can vaporize if I give this number. What you can do, you can use this as a conversion factor. So this you can write as 14.7 kilojoule over 1 mole, and or you can just reverse this depending on the problem, which one you want to use, so that we know like very similar as density. Right. So these two fractions, conversion fraction, and what we studied since chapter 1 and 2, we call them conversion factors. Which one you use depends on the other quantity. Now this time we give you the other quantity is 155 kilojoule. And you want to find out the mass in gram. So therefore you want to cancel, you somehow want to cancel it out. So that means you want to choose the second one, the second conversion fractions. Alright, so you probably already did. So if you do that, and you will see this become come out. Now you have the mole, and obviously the question asks you the gram. Now we know I assume you are able to know how to convert from mole to grams use mole mass. 1 mole of H2O and will be 18.02 gram of H2O. So more come out, and you do the calculation, and you find out how many grams. Right, so I take 155 divided by 40.7 times 18.02, and I get 68.6 and gram of H2O. Right, so that's one example, and so we'll use this chapter, you will see those paper like those calculations. Right, so this one is opposite, and now you have this number. Remember, you have to check this number, what this number means. Okay, this number is sort of the height of vaporization. And by the unit, it tells you to vaporize every 1 mole of material, it will require this much of heat. Right? Now the question is, how much heat do you need to vaporize this? Right? So what you can do is, if you want, you can write this number as 2 fractions again, see which one you're going to use. Okay? So you will see that is 40.5 kilojoule per 1 mole, or 1 mole is 40.5 kilojoule. Okay? Now the question is, you want to find out how much energy, maybe kilojoule here or kilojoules, but multiple choice. Okay? And the other question will give you 98.6 gram of this guy. Okay? And so you have the gram pretty much the same as mole. What you can do, you can convert that into mole. Okay? So you will see you have 2 carbons, so therefore 2 times 12.01. What I'm doing now is calculate the mole mass. Altogether we have 6 H, so therefore 6 times 1, 1. And we have 1 O, so therefore it's 16. Right? So now this is the mole mass, so therefore it's 1 mole. Right? And so you can't, so this will be the gram. I put this in parentheses, the gram. So gram and gram cancel out. Now you have mole. Right? Now because you have mole, so therefore I'm going to use the first fraction. So I have 1 mole and 40.5 kilojoule. And that's it, so I'll count out the mole, again about how many kilojoules. And you do the calculation, right? Let me see, we'll do the calculation what we get. 98.6 divided by 2 times 12.01. Don't forget to use parentheses in your calculator. Plus 6 times 1.01. Plus 16, okay. And then you times 40.5, so you get 86.7, 86.7, the unit is kilojoule. Right. Okay, now we talk about the dynamic equilibrium, so I mentioned that briefly. When you have those vaporization, condensation in a closed container, so it's closed, so you at some point this goes up, goes down process will become equilibrium. That equilibrium means you have the rate of that two, or the speed of going up and going down are the same. It does not tell you you have the equal amount of liquid or vapor. Okay? That obviously are not the same. So you probably have a lot of liquid and less gas, or vice versa. You don't have to always have the same amount of liquid and same amount of vapor to have the dynamic equilibrium. What is required for this equilibrium is the rate. And as we said, there are many different ways you can we can use to tell which one has the stronger intermolecular forces. We can use boiling point and melting point. Then we know the higher the boiling point, the stronger the intermolecular forces. And now you can also use the vapor pressure. So the vapor pressure is about measure how easy those molecular or atom will change from the liquid into the gas. So therefore, the higher the vapor pressure, okay, and the weaker the attractive force. The weaker the attractive force is, the higher the vapor pressure. So you can use that. And then we also know for the same material, and we can change the temperature of the liquid. And then we change the temperature of the liquid, and there will be more percentage of the molecule that can change, can vaporize. So therefore, when you close the container, and you will have a higher vapor pressure. And that again is similar to what we did in the lab. We move that flask that has the messenger from beaker to beaker, and you can remember probably the vapor pressure getting higher and higher when you move them from colder to the hotter water bath. So a lot of scientists did some of those measurements. For example, they measure a different material at a different temperature, what are their vapor pressure, and you can see they all follow the similar pattern. Looks like very good parabola and or exponential function, and then this middle one is water. And so again, you can see this table you read like this. So this horizontal axis is temperature in Celsius. That is the vapor pressure. And we know what we mean by the boiling point. Boiling point is when the temperature of the liquid getting high enough, then your vapor pressure equals the external pressure. Now the normal boiling point, normal external pressure, like the normal air pressure, is 760 millimeter mercury. So therefore, the boiling point at this pressure, at this external pressure for those different compounds, is sort of the normal boiling point. And you can see the normal boiling point for water when you draw this green line and come across with this red line is at about 100 degrees Celsius. I will leave a little off, but that is how we get this normal boiling point. And then we can see the normal boiling point for that ethanol is lower than the water. Again, for ethanol, so you have like a little weaker intermolecular forces compared with water. Right. So if you have the data, you have those data from your lab, you have those data, which means the data number for the vapor pressure, for the messenger, and also the temperature for that vapor pressure. You can do a data analysis like this. And what you do is, as we talked about briefly in the lab, you take the temperature, change them into kelvins, then you take 1, divide by the temperature in kelvins, so this will be this axis, and that means your higher temperature will be on this side, because you take 1 divided by a higher temperature, you get a small number here, and then your lower temperature will be here. We know from the last slide, when the temperature is lower, your vapor pressure is lower for all the solvents. Right, so then if you don't use those pressure, vapor pressure directly, you don't use the temperature directly, you use 1 over the temperature in Kelvin, then this is the logarithm, maybe the log or the ln, so you have this. Right, so then you have those kind of curve, and this is pretty much a straight line, and you have the slope, negative slope. Okay. Those kind of lines have negative slope. So then what you do, you take the slope, whatever slope will give to you, then you change the slope, so slope here is negative, then you're adding a negative, so therefore negative here become positive, then you times R is the gas constant, but when you calculate those energy, you use 8.314. So this will be the way that we can use to measure the so-called heat of vaporization delta H VAP. And from your data for the messenger, you do the similar measurement, you can calculate what is your delta H. Then you look up at the online or some of those textbooks, you will see whether your number matching those numbers. So there's a relationship between the vapor pressure and temperature in Kelvin. So that means those logarithm pressure and those one over the temperature, those relation can be simplified if we don't have too much data. If we only have 2 points of data, we can use this formula. You probably are going to study this more in Chem like 1 or 2. So again, the boiling point is the point when the vapor pressure of the liquid equal or become the same as the external pressure. Okay? When the external pressure and the vapor pressure are the same, then your vaporization process, not only from the surface, it's everywhere. You see the inside also have those bubbles. Those bubbles is actually those vapor of the liquid. If you have water liquid, then those bubbles pretty much completely all those water vapors. So the boiling point is the point when the vapor pressure becomes the external pressure. The external pressure, that means air pressure. That depends on many variables, depend on the weather, depend on the location. For example, here it depends on, we have these few places, location. At the top of mountain Everest is so high, and the air pressure, the external pressure becomes so low, so therefore your water boils at 78 degrees Celsius. That is dramatically low. It's not because water have something change, become something else, it's because the external pressure is low. And so let's see which of these following statement is true. Vapor pressure increases with temperature. That is true. Hydrogen bonds are stronger than covalent bonds. That's not true. We know hydrogen bond. When we talk about the hydrogen bonds, it's not really. So remember this hydrogen bond. When we talk about this hydrogen bond, it's not H to H bond. It's not that. It's a bond is bound by something like this. One example is this E to O. Then you have another O and H. This dotted line. So it is this. So this is this dotted line. So it's not a chemical bond. And now we see C. Intermolecular forces hold the atom in a molecule together. No. Intermolecular forces can hold the atom together into a bulk material. Or can hold molecule into a bulk material, into like a liquid or into like a solid. So the forces that hold the atom in a molecule, forget about that part, only this part. From here, forces hold the atom in a molecule together is a chemical bond. So that's not true. So C is wrong. These opposing forces are generally stronger than dipole-dipole forces. Generally, that means relatively. So that's not true because we know this relative strength. So this slide is about place the following substances in the order of increasing boiling point. So as I said, you want to put them in increasing boiling point, you pretty much find out the increasing magnitude of intermolecular forces. Intermolecular forces. So this part equals increasing molecular forces. Then you have exam what do they have? So we have this three molecular. We have three particle. So this is atom, and then we have this Cl2. So we have this O2. O2, that means you have oxygen bonding to oxygen like this, right? And Cl2 is like this. Right? So let me circle these two molecules. Then both of them are nonpolar. Okay? Now atom obviously is nonpolar. Okay? So therefore all nonpolar. All nonpolar. Or all of them only have what force? Only have this Persian force. Right? Then this Persian force depend on what? This Persian force only this Persian force depend on that. Okay? Some other maybe depend on, but we don't use this. This Persian force depends on molar mass and the shape. Okay? I think these three particles, one atom, two molecules, roughly have the same shape. Okay? The shape is not a problem. Now you have to think about what is the pattern for the molar mass. Okay? You use the shape, that also comes with the same result. Okay? And then the thing becomes simple. Okay? Linear molar mass is about 20, right? So 20 molar mass and 32, okay? And about 70. Okay? So therefore, this pretty much the last one pretty much is just let me see. Yeah, last one is pretty much the pattern. Okay? Increasing strength of this Persian force, and that is the only intermolecular force. So therefore, increasing pattern for the boiling point. Choose the substance with the highest boiling point. Okay? So this first one is non-polar. Therefore, only this Persian. Okay? And this one is ionic. And you have a chemical bond. Chemical bond, not intermolecular forces. Okay? This one, non-polar. This one, polar, and it can H bonding. And that one, non-polar. Right? So even though you see this D is polar and also can handle bonding, but so that gives you the relatively stronger intermolecular forces, even though not the strongest one ion dipole. But all those intermolecular forces is weaker than the chemical bond. So one of them have the chemical bond because this Ki is ionic compound. Then you know, in the bulky ionic compound, you will have a lot of those ions, the plus ion, negative ion. And those attraction between those ions is so strong that makes the boiling point much higher than all the other four. Okay? And so then the last section about second section is about the heating process of some of the material. Okay? So in general, we're thinking about when you're heating some material, what change, what can happen? Will the material change the state or simply warm up? And usually we're thinking about the three states: solid, liquid, and gas. Like in my example, we can pretty much like think about the process go from the coldest point to the hottest point is like this. Try to calculate what is the total energy for heating 1 bar of H2O from negative 20 degrees Celsius to 125 degrees Celsius. Okay. So this is a very complete example. And in the test on the exams, I probably not ask you to do so much calculation. I will just choose like 1 point and starting from some liquid and calculate how much energy do you require to change into gas or so on. So we'll see some of those examples. But for this process, you pretty much just see all the possible calculation you're going to use on the exams or on the quiz. So again, on the exam, on the quiz, you probably will not use all of those calculations here in this example. Okay? Right. So pretty much you want to calculate the energy or the heat. Okay. And when we study in Chapter 6, and you can see about 2 formulas you're going to use for those possible steps, and we label in this graph 5 possible different steps. Okay? Step 1 is about heating those solid, and step 2 is about melting the solid, and step 3 is about heating the liquid, and step 4 is about vaporize the liquid, and step 5 is about heating the vapor. Okay? So this program, you start with negative 25 degrees Celsius. Then obviously that will be the liquid, I mean the solid ice for H2O. So this will be our starting point. Okay? And then you are heating, keeping volume of energy, and then your water will melt, I mean your ice melt, your water vaporize, and water vapor become even like hotter, become like because when you vaporize the water, it's at 100 degrees Celsius. Then you're going to keep adding heat, then your water vapor become like 125. So therefore your finish is somewhere like here. Okay, see here, and here, the 125. So here will be our finish, our end. So you have to calculate all the way how much heat you need to go from here and here, and so on all the way to here. So then in those different steps, step 1 for this line, step 2 for this, step 3 for this, okay, you are going to use different formulas. You might use the same type of formula but different numbers. Okay? Okay, for this one or this one, okay, so these two like the horizontal line, okay, are the so-called phase change. You use let's see, heat equals the delta H times something times N. Okay? Delta H. Now the delta H depends. For this one will be delta H vaporization. Okay? So this side this part. And for this one there will be delta H fusion. How much heat you require to melting 1 bar of the ice. Okay. Now for the other 3, okay, so let's see, for 1, 3, 5, you see heat equals what we learn in Chapter 6, okay, is using those heat capacity and temperature change. And usually you use the specific heat capacity, which means C of S and delta T. Okay? So I just write out the general formula, and for this one, I did not write delta H or what here. Okay? And then similarly here, I did not write CS of what. Okay? So you have different delta H for the melting and compare with vaporize you have different CS for ice and compare with liquid water and compare with water vapor. Okay? But in general, they have a similar format. For 1, 3, 5, use this kind of format. Okay? For 2 and 4, use this kind of format. All right. So let's see the calculations. Okay? We will go step by step. Okay? For the first step, you're going to use this one. Okay? That's the first step. Okay? You're going to use mass times C of S times delta T. Okay? Now mass is gram or kilogram, depending on this guy. Okay? Remember in chapter 6, we see this specific heat has the 0 on the top, then both of these at the bottom. Okay? So usually it's easier to read is same as 2.090 over gram times Celsius. Alright, so then it's a straightforward review what we learned in chapter 6. So you have this formula and then just apply those numbers in. You have 1 mole, which means 18 gram. Remember, you have to check what CS you use. Okay? Now this process is changing the ice from negative 25 to 0 degrees Celsius. Okay? You don't turn. So before you turn, you have to make sure you don't turn. You turn, you don't use the different formula. Okay? So for each of those straight line, and we go back to the last slide. Okay? For each of those straight line, and without those binding point, use one formula. Okay? So once you change from one line to a different line, from one line to a different line, you think about use different formula. Okay? Now here you go from negative 25, so on the picture is somewhere there. So you have negative 25 here, okay? And go all the way to 0. So both of them is Celsius. Okay? So just consider this segment. Okay? You did not go through that line yet. Okay? Okay, so then we will consider the temperature change from negative 25 to 0. And we said before, delta T is the final. The final is 0, your initial negative 25. So therefore, your delta T is 0 subtracting by negative 25. Okay? Again, don't forget to check what CS you use. So this example, this step is the CS for ice. Right? So therefore it's 2.09. And you should be able to get this number from the last slide. Right? One more point. So once you have those three numbers multiply, gram comes out, Celsius comes out, so this Celsius both this Celsius out. Then you have the joules. And here you have the kilojoules. You know how to change from joule to kilojoule? Divide this number by 1,000. Okay? So that's what happens. And so then you will go on to the second step now. So let's say we going from here to here. So this is negative 25. This is 0. Okay? So that is step 1. Okay? And that is history. What we did is on the last slide. Okay? Now we're going from here to here. And so here, this point is also 0 Celsius. Okay? But the difference is this 0 Celsius here is the ice. And this point here is 0 Celsius, but it's water. Okay? So this process, without any binding or turning, you use one formula. So those called horizontal. So this kind of very flat. Okay? What you use is those kind of format. N means mole times delta H. Okay? Because usually the delta H is given to you by per mole. Right? So that becomes simple. You just identify delta H what? Right? So if the process is melting, we use delta H fusion. And from that slide with all the pictures, we have that delta H 6.02 kilojoule per mole. Right? And so very straightforward. We will take this one more because tell us we have this one more material, and then we have this number is for delta H fuse. Fuse means come together, which means melt. Okay, because you have ice cube, melt is fused together, become liquid. And so now we finished the first two steps. We go to number 3. Okay, now let me calculate adding on. So I have this here, negative 25. Okay, now here is 0. Let me draw like that. Now there's 0. So this is our number 1. This is our number 2. And number 3 is this part. So here's also 0 degrees Celsius. Now this point, in terms of temperature, it will become 100 degrees Celsius. Now between this point here, the material is the same. Obviously the same material as your 82O is also the same state. Okay? Now here is liquid water. Here is also liquid water. What the difference between here and here is different temperature of water. Okay? So we can think about here is the water just from the melting ice. Here is the water just ready to vaporize. But the vaporize takes time, take energy. Okay? So you just go like adding energy, the ice ready to melt. Adding more energy, all the ice melts. Okay? Then adding more energy, all the ice water, all the cold water, 0 degree water become like warm enough, ready to vaporize. Okay? So even though before it vaporized, so like all vaporize everywhere, still some vaporize, but we don't have to consider those small details. Right. So for this step 3, now here we are with step 3. Let me change the color. We'll change the color before the last two slides. So this is number 3, which means the one you want to calculate right now. Okay. And for those kind of slanted line, okay, the pattern you use is mass times CF, C of S times delta T. Okay? So the only difference is the possible the C of S and the delta T. Okay? Now your delta T obviously was the final temperature minus initial temperature. The C of S depends on the state. Okay? For water, the C of S is 4.18. Okay? So once we know these two numbers, and our mass is still the same because we have 1 mole is 18 grams for 82O, and now this CS is different than your first step. Your first step is 209. Okay? The temperature change is also different because for this particular step, we consider all the way starting from 0 degrees Celsius to 100 degrees Celsius. So therefore, final is 100, initial is 0. Okay? So this part is delta T. Right? You get joule first, then divided by 1000 or 10 to the positive 3. So this guy gone. So that's about a kilojoule. Alright, so now we will keep going and go on to the step 4. Okay? Okay, let's review what we did. Let me change this. So what we did before is let's use red. Okay? So we starting from negative 25 to 0 and to 0 again, because this 0 here is water. Then we change to 100. And now we're going to see like what we do right now. And what we do right now, let me use yellow. And this is also 100 degrees Celsius. 100 degrees Celsius. Now what the difference for this step 4 between this starting point, final point, is both of them have the same temperature. Okay? But this point is 100 degrees Celsius hot water, liquid water. This point is 100 degrees Celsius water vapor. Okay? So how you go from this to this? You add in heat. How much heat do you need? Okay? And you use this format. Use N times delta H. Okay, now let me number those steps. So this is step 1, and this is step 2, this is step 3, this is step 4. Right? Okay. So this step 4 becomes a horizontal, flat. Okay? For the flat one, use this. Right? So you have to see delta H what? Okay? For this one, for step 2, delta H, we can write here. So delta H fuse. So here you used for step 2 is delta H. Oops, I want to use the red. So delta H fuse. Right? Now here for step 4 is use delta H VAP. The delta H vaporization. Alright, so once we identify these two and we see the delta H fuse, I mistype here. So the delta H fuse is like a different number, 6 something, and delta H, there's a typo here. So this will be VAP. Excuse me for that. So then we can use this number, okay? Because we need the delta H VAP. So delta H VAP is 40.7, and then that's the kilojoules. So you don't have to change that. So more and more come out, you get the amount of kilojoules. Right. So then with the last step, okay? Review what we did. So we're starting from let me use negative 25, this is 0 degrees Celsius, negative 25 degrees Celsius, then we melt at 0 degrees Celsius, then we heat to 100 degrees Celsius, then we heat and vaporize 100 degrees Celsius, vapor 100 degrees Celsius, liquid 0 degrees Celsius, liquid 0 degrees Celsius, solid, and negative 25 degrees Celsius, solid. Right, so now the number is here is 1, and here is 2, and here is 3, and here is 4. Now we'll start on the number 5. Okay? What's in number 5? Number 5 here it's 125 degrees Celsius vapor. Okay? Right. So what you can see for step 5, then numbers is step 5, is starting from 100 degrees Celsius vapor and changing to 125 degrees Celsius vapor. Okay? So you did not change the state. If you don't change the state, or those slanted line, use this type of formula. Okay? That is the formula we studied in Chapter 6. If you change the state, okay, here is liquid, and here is vapor, so liquid and gas, solid and liquid, you use, therefore, 24, you use N times delta H. N times delta H. Okay? Now tell me, for this one, you use delta H what? For that one, you use delta H what? Okay? So for this one, for number 4, you use delta H VAP, like what you said on the last slide. For number 2, you use delta H fuse. Okay? So there will be different numbers, but a similar format. Right? Now let's finish this calculation for step 5, which is very simple. Just pay attention to this number and pay attention to how you get this, because mass is for the same material. We don't like consider any loss of the materials. Right. So let me list those. What do we draw? And we use that format: mass 18, CS. Now see the number. Okay. For liquid is 4.18. For this gas, so even though this S not mean solid, it's just specific. Okay? We have this number. And then you know the temperature change is final temperature. So 2 is to the final, and that. Okay? So again, you need to get a joule divided by 1000, move the daily point 1, 2, 3 times, you get 0.904 kilojoule. Okay? And then the total energy, we're starting from that -25 all the way -25 degrees Celsius ice all the way to 125 degrees Celsius vapor. We have that is the 5 step. Okay? The heat of heating the ice from 25 to 0 degrees Celsius. Then the heat of melting the ice. Then the heat of heating the liquid water from 0 to 100. Then vaporize the water. Then heat the water vapor from 100 to 100. So altogether, you get these 5 numbers added together. Okay? This will be the complete calculation for the so-called heating curves. Okay? For the cooling curve, we do the opposite. Okay? And similar, so you get all the numbers will become like negative numbers. But in the test or exams, so you probably will not see all the 5 numbers, all the 5 steps, depending on where we start. Let's see this example. For different material, but similar, usually material will go from solid into liquid into gas. Let's see what is this problem about. Starting from what and go to what? Go through how many steps? Okay? Remember, each one chain of those binding or turning just contains 1 step. Okay? So the problem is we have this much mass. Okay? Let me change the color. So this is our mass. Okay? And let's say starting from this. Right, let's start. And tell you what is state. I said liquid. Well, that's straightforward. Tell you it's liquid. You like from 35 degrees Celsius, this amount of liquid, right? And then to gas. But this gas, this will be the gas. And also be very careful. This like is also our normal boiling point. It's very important because change the gas into water temperature. If you just change your liquid to the gas still at the normal boiling point, which means you did not really heating your water vapor yet. So let's draw that heating curve, and you have this. So let's say this will be our starting point. And we see that is 35.0 degrees Celsius. And then our ending point, let's see, it will be this 76.8 degrees Celsius gas. So gas. And this 76.8 Celsius is also our normal boiling point. So therefore, for this particular problem, you don't have all the 5 steps. You actually only have 2 steps. And if I call this our, if I want to mention those steps I use in the example, so this will be our step 3. And this will be my step 4. Okay? So I don't have step 1, step 2, and step 5. I only have the step 3, which is more part of the step 3, not all the step 3. Okay? So I will have that part of step 3 and step 4. Right? So for 3, okay, is heating liquid. No phase change. Even though the whole program has a phase change, but only for step 3, the phase not changed yet. Okay? So what you do, and you will use heat equals m times Cs times delta T. Okay? So then you tell me what Cs shall we use, and how we calculate delta T. so the mass is straightforward. So we have 25 gram, right? And now CS, shall we use what? Shall we use the CS for the liquid, CS for the solid, or CS for the gas? Right, because there's only one number given to you, right? And which is CS, specific heat of liquid. Therefore, you can use 0.857 joule per gram per Celsius. Right? So then you probably tell me what is your delta T? How you find out delta T? Okay? Well, delta T is, let's say you start from this. Starting this temperature is 3500. Then you add in here. You don't add in, well, even though you add in there, it's still the same temperature, but sometimes if you're adding point somewhere others, you don't use like the final, right? So just use this temperature that don't have the phase change yet, even though it's ready for the phase change. Okay? So therefore my delta T I will write here, it will be 76.8 minus 35. And both of them have Celsius. Right? So you just calculate 25 times upon 85.7 times the difference of these two numbers. That will give you how much joule. Okay? And because all the answers is kilojoules, so you have to divide by 1000. Okay? So I take 25 times 0.857 times 76.8 minus 35. Right? So I get 895.6. I don't mind number R is the amount of joule. Okay? Now this is the same as 0.8956 kilojoule. Okay? So think about how I get that number. Right? Right? So this is the one part. Okay? And let me write it down here. Okay? I try to use as much as possible of PowerPoint, but that's much easier for you to see. So our heat, let's say heat of heating the liquid is 0.8956 kilojoules. That's only one part. That's only the first part. So that's from that part 3. Okay? Not all the 3 steps have the examples. Well, step 3 in the example is from like the liquid right after melting, then all the way to the liquid ready for the boiling. Okay? Now let's erase those and think about. So we're starting from here to here. So this is 35.0, 76.8. And this also 76.8. Okay. Now here is liquid. And here is liquid. Okay. But here is gas. Okay, so this is the part of 3, and this is the 4. Okay. So you already see that heat for 3 equals 0.8956 kilojoules. This is the point. Okay. Heat for 4 use what? Use what pattern? What format? I think you get it, right? Use N times delta H. Okay? N is more. So N is more. Okay? Usually, because those numbers give you is per mole. Per mole. Okay? Now you tell me which number should we use. Should we use 3.27 or use 29.82? Right? So this number, if I solve that, equals what? Fusion. Now this number here It's called what? Vaporization. Okay? Vaporization. And now let's see what does the step 4 do. That depends on what you're starting from, what you're adding up. You started from liquid, adding to gas. That means vaporization process. Okay? So therefore, if this is the vaporization process from here to here, it vaporized. Okay? So therefore, you can use the heat of vaporization. Use this number. Okay? So I'm going to use N times delta H VEP. Now we have just find out what is our N. Okay? N, we have the gram. Okay? You want to find out N, what you use? That's in N equals 25.0 gram times, okay? Whatever the molar mass. What is the molar mass? Well, that's usually we would get that. So that's 12 plus 4 times 35.45. But that is for CL. Okay? Right. So you do the calculation, and let's see. If I only calculate this part first, so I have 12.01 plus 4 times 35.45, and so this is 25.0 gram times 1 more over 153.8, and this is also gram, and sort of gram, and then this gram comes out. Okay? So then 25 divided by this number, and get 0.163. I round up one number more, right? Well, now that's become simple. Now this number, and then I go this way, okay? 0.163 more times, and for every one more, this number. So 29.82 kilojoule over one more. That comes out. Okay? So we will have 0.163 times 29.82, and get 4.86 kilojoule. Right? So then what is your final answer? What's the final answer? So you are adding them together. Okay? Adding them together. Okay? So then 4 is the heat of vaporized 25 gram. That equals 4.86 kilojoules. So then the final results for the total heat equals 0.8956 plus 4.86. I don't know what that's come out to. 4.86 plus 0.8956. 5.76. 5.76. Well, a little off than C. Well, that's close. Okay? Right. And so then this problem is similar. Okay? This problem is similar. Let's see what's the starting point, okay? And how much energy do you need. You read the question, you will see it's starting from 36 grams of H2 as liquid. 6 grams of H2 as liquid at this degree Celsius to this amount of gas. Now this probably have more steps, right? So let's see let's draw those points. So we have here our start at 65 degrees Celsius, and we know that the liquid. Okay? So you're starting from liquid, and you're heating the liquid and your liquid will increase the temperature, right? Now we know once you change into once the temperature becomes like 100 degrees Celsius, that's going to the usual, because we talk about this normal, right? So here even it's still liquid, but it's ready to boil. Okay? So again, this will be our part of the step 3. Okay? Now once you have more heat, and this is also 100 degrees Celsius, well, that will become gas. If you add more heat, okay? Now your gas, I draw that another proportion of this 115 degrees Celsius gas. Right, step 3, and step 4, and step 5. Okay? Right, so we have more steps in this program. Okay? So step 3, okay? Step 3, heat for 3, that equals that pattern, M times C of S times delta T. Okay? Mass is 36.0 gram. C of S, think about what C of S we use and how you calculate that delta T. Right? So C of S, you said use the liquid. Yeah, because you are going to use the liquid. That's for the liquid part. Alright, now temperature change. Your final temperature 100, the initial temperature 65, and both have Celsius. But that's it. So you have to be careful to see what CS you use and what your temperature change. And then what you get is joule. Okay? And all those are kilojoules, so don't forget to convert into kilojoules. Okay? So you have 36 times 4.18 times 100 minus 65 become like 35. So you get 5266.8 joule. That's same as 5.27 kilojoule. That's gone into like 3 sig figures, right? So I'm going to continue with heat for 4. That equals what pattern? That equals N times delta H. Now delta H what? Because step 4 is changing from liquid here into gas. So that's a vaporization. Okay? So therefore it's VAP. Okay? And how much more is this? So I'll just do a very quick calculation. That is 2 more. Right? Because molar mass of water is 18 grams, you have 36 grams, you have 2 more. I'll skip some of the steps. So you have 2 more here. Okay? And then delta H VAP. Delta H VAP. Delta H VAP is here, right? 40.7 kilojoule per mole. More comes out. So that's good. So you have 81.4 kJ. Alright, so then we come about heat for 5. Now go back to this formula. M times CS times delta T. We still have 36.0 gram. Now you think about what is CS and how you get delta T. So let me change back to this. Okay, what do you think? What CS should we use? You said it's for the gas, right? So here is the gas and the gas. So therefore, gas 2.01 joule over gram and Celsius. What about the temperature change? Well, depends on your final temperature, initial temperature. So that's your final, and that's your initial. Therefore, it's 115 minus 100, and both of them Celsius. Celsius comes out gram Brown kind laws, you should get how much joule, right? So 36 times 2.01 times 15, because that's 115 minus 100. You get 1085 joule. That's same as 1.09 kilojoule. Right. So what do we have like all together is this amount of kilojoule, this amount of kilojoule, and this amount of kilojoule. Okay. So I'm going to write them out here. 5.27 plus 81.4 plus 1.09. Okay. So all those together, 1.09 plus 81.4 plus 5.27 is okay, so those numbers, and you use some of those over here. Okay, so now adding together give us 87.8 kilojoule. You can leave it off compared to the numbers. Alright. So then the last section is about the phase diagram. Okay? Phase diagram describes the different state and state change that occurs at various temperature and pressures. And here are two like examples of phase diagram. Typical simple materials looks like that, okay? And water looks like this. Okay? So phase diagram usually is two-dimensional. You use temperature on one axis, pressure on the other axis. Okay? And so therefore you will see that it describes different states and state change that occurs at various temperature and pressure. Okay? So then area, so those are called area. Area representing state. So solid in this part, liquid in this part, gas and so on. And then the line. So we talk about those red line, not those dotted line. The red line, red line, red line. So each red line representing those different things, different those equilibrium. For example, this red line here is cutting between the solid and the liquid, so therefore it's representing the equilibrium between solid and liquid at different pressure and temperature. So again, in other words, this red line here representing the melting of solid to liquid or freezing of liquid to solid. You have this line here. This line representing the boundary between liquid and gas, therefore representing the vapor pressure line, or the vapor, or the vaporization process equilibrium, or the condensation process. Now similarly for this, because this line here, this little kind of like a tail here, starting from this point to this, is the boundary between solid, that is still solid, that line just tells you that's some special point. Solid and gas. So this was representing the sublimation. And then we will talk about this special point that is indicated by this two dotted line there for the pressure, dotted line there for the temperature. So this, by the name, is so-called a triple point. Triple, which means you have all the three states coexist. You probably not see those kind of phenomena. You see this in one picture for the three states that coexist. There's a significant ice, significant vapor, and significant of liquid. So they all exist in the same at the same pressure, same temperature. And then for most of the material, for the typical material, so the freezing point increases as the pressure increases, and you can see here, if like the one pressure is here, okay? The one pressure is here, okay? And you have this freezing point. If I call this P1, okay? And I have called this TF1. Okay? If I increase the freezing point, I call that P2, and I have this TF2. And obviously TF2 is higher than TF1. So that's what this sentence tells you. But for liquid water, that's just, for water, it's kind of opposite. Okay? And this again is another example of a phase diagram. Okay? Area for state, area for another different state, area for another different state. The line is between those state change, from liquid to gas, or from liquid to solid, or from solid to gas. And this is sort of the vaporization process from liquid to gas, a condensation process from gas to liquid. And this curve is called the vapor pressure curve. And that's the fusion curve. And go from solid to liquid melting, from liquid to solid freezing. And you have this sublimation curve. You go from, if you go directly going from solid to liquid without going solid to gas without going through the liquid, you have the sublimation, and vice versa. If you have the gas directly going to the solid, you have the deposition. And we talk about Tuesday, example is the frost, and example of that is disappearing of the ice cube. And then one point here is not, even though this is not a good phase diagram, they call the critical point. Okay? What do we mean by the critical point? Critical point, you can think about it is, if you go to the critical point here, you go down, and you have this TC. And then this TC is the critical temperature. That means if the temperature is higher than this, and then you cannot change the gas into liquid. In other words, if the temperature beyond the TC, which will be different for different material, then there is no difference between the liquid and solid. And then we talk about the normal something, okay? Normal boiling point, normal freezing point. So then what you can see is normal boiling, that means the external pressure is 1 atm. So that word is 1 atm. Okay? So here is 1 atm. Because that is the normal, is our normal external pressure. And when the vapor pressure becomes same as external pressure, then we have the boiling process. Okay? And then if our external pressure is normal, which is 1 atm, then we have a normal boiling point. Normal boiling point, it will come out across with this, the sort of normal boiling point will be here, normal melting point will be there. Normal melting point will come across with the change from solid to liquid, okay? And normal boiling point here is change from liquid to gas. You can navigate through the phase diagram like those. Usually when you navigate, you just go either horizontally or go like vertically. Okay? Or you go step by step. You go one step, go like that, then go step like that. Okay? See like what will happen to your material. Okay? Let's see, for this process A, we can think about going horizontally all the way doing that. Okay? So imagine this is your starting point. And then use your starting point obviously in an area. Okay? And in this area is solid. Okay? So when you go in horizontal, which means your pressure are not changing, and you only change the temperature. Okay? So what happens, and this will be the typical like for water. So what you can see is you start from ice at 1 atm, And as we know from our daily experience, so we heating, which means we increase the temperature, so the ice melts, change into liquid, and that will be similar to those calculations for the heating curve. Then you're heating the liquid, and once it becomes those boiling point, for this example will be our normal boiling point, 100 degrees Celsius. So you know, like change, began the phase change. So then once you apply enough heat, then all those given liquid will be vaporized, and they become all those liquid. Okay? So this is this A line. The B line is, let's say, starting from this point and go over somewhere here. So then you just identify what will be this point here. Well, that point is not on a line and not on a point, it's on an area. This area is liquid, right? So what happens is, so you start from that part that of liquid, that means 1 atm, about 25 degrees Celsius, okay? And you go down the line, that means you don't change the temperature. What happens, you go down, the pressure getting decreases, getting less and less. Okay? What can that happen? That means the external pressure. Okay? And so then once you change the external pressure so low, so you change that in, become the vapor pressure of the liquid, of the water at 25 degrees Celsius, then that can also have, the boiling can also happen. Okay? But that boiling point is not our normal boiling point for water. Our normal boiling point for water is 100 degrees Celsius. But for 25 degrees Celsius water, you can also boil, but your pressure, or your air pressure should be much, much low, not like 1 atm. So this point here is the transition of the state, or the phase change from liquid to gas. And if you continue to decrease your pressure, then all your liquid will become gas. And then if you continue, then pretty much nothing happens. That means your gas has like more and more volume, so it's kind of like a Boyle's law. Right? And so that's, again, see this phase diagram has a little better critical point. See, like beyond this point, and you don't see the difference between those liquid and gas. Right? And so this compares those little different navigations. So that's separate. You can navigate with that, going up, going horizontal. Right? And let's see, for particular for these two, and what you can see is that you're starting from this point on this E process. You're just starting at the line, which means the boundary between the liquid and the gas. And if you like, let's say, you increase the pressure, and so then obviously all your gas will become liquid, because you're starting from here. You're on the boundary between gas and liquid, and then you increase here, become all liquid. Then you get more and more dense liquid. For this type of material, at some point, it will become like freezing, and then all of them become solid. Right, for this process, for this B process, you start from this point. Now this point is not similar here, you started on a line, you started on an area. And this is a solid area. Okay? So you keep the pressure the same. You increase the temperature. So now what happens for this scenario, you don't go through the liquid, you will change from solid, right into gas. And this kind of process called sublimation. Right? So let's say this CRE, I give you this phase diagram, okay? And then ask you consider the following phase diagram for one of the special material. Which of the following is true? Okay? So this is one ATM line here, this dotted line. Okay? At 1 ATM, Well, this UF6 boil, which means you have to go from the liquid to the gas. And this line does not cross this line here. Right? Well, it melt means you will go from solid to liquid. It doesn't go across this line. Right? It's sublimate. Sublimate means you go from solid to gas. And this is what happened. Right? So you miss like one like word for state, and here is the gas. Okay? Right, so therefore, you see at 1 atm, what can happen is either this material go from gas to solid, deposition, or from solid to gas sublimation. Right? So that's what can happen. I think that's the end, and I will let you know what we will do like about this chapter. We either will just watch the video, or we will make out that this lecture, we will do the lecture again like Tuesday, and I will send you an email and let you know.